All right, section 5.2 begins on page 274. The title is Definite Integrals. We're actually going to start calling this summing business integrals. However, two things. First of all, set aside for the viewer, you're not going to see me much. I'm going to be talking a lot, so listen. And sometimes I will come to the board, but not very often. And the other thing you guys all need to remember that are learning this, listening to this, whatever, is that we aren't actually going to be doing any integrating. Not today. We're going to be learning about the integral and what it does. But we are not doing any integrating, so get over it. Okay. Definite integral, they have a definition for you at the top of page 274, but it will quickly become obsolete. What it says is that a definite integral is a sum of a whole bunch of things, and we've already summed up the areas of a bunch of rectangles, right? Yeah? Whose heights were determined by some function. We added those up, and we said that that was an estimate for the area under the curve. That area as a number associated with how much space it takes to paint that. For that area, that number is the integral of that curve, and we estimated its integral. Okay? Now, it's going to get more convoluted than that. It's not quite that simple. You'll notice on the next page, on page 275, I just want you to look at the pictures. I've tried discussing the details with people. They didn't get it. It took too much time, and it was worthless. So I just want you to look at, in general, what's going on. That big picture in the middle that's got that blue curve going up and down has pieces of it that are above the x-axis and pieces of it that are below. And the ones that are below have rectangles associated with which are brown. And the ones above are blue. Now, to find the values that are associated with the area of the brown rectangles, can you understand that you would have to multiply a width times a negative number? For the purposes of our discussion then, even though it's not really a true thing, it can't actually happen, we will call that space negative area because of where it is. All area is positive. Okay? But we will refer to that portion between the x-axis and the curve where it's brown, we will refer to that portion as the negative area part and the blue as the positive area. If that's okay. Okay? Understanding that when we paint something, we don't ever paint anything negatively. If you take the negative number associated with the brown space and the positive number associated with the blue space and combine them together, you have the integral for that curve. And it's a pretty small number because the brown and the blue area are fairly close together, but I believe by glancing at it that the blue is slightly larger. Which means when I combine those two numbers together, one negative and one positive, I will get a pretty small positive number. Am I making any sense to you? Okay, so when we talk about an integral, we're talking about positive and negative space, if you will, combined together to get a total which uses positives and negatives, and that would be called the integral of that curve. That small number would be the integral for this curve from A to B. Okay? Is not the area. That's a different concept, but the integral of that curve from A to B is that small number where we combine the negative and the positive. The area is far bigger. So it's far bigger than the blue if we talk about paintable space. We'll reconcile the two in a little while. I just need you to understand the difference between the concept of area, which is how much paint it takes to cover it, regardless of where it is, and the concept of integral.
So the brown is still negative?
Yes.
Okay.
For the integral, the brown is negative.
But for the area?
But for when we want to find area, when they say find the area of between the x-axis and the curve, that's paintable space, and we would turn the negative area positive
So the
to add it to the blue.
integral is the after the negative area and the positive area added together.
Yes, it's what we would call, if you will, net area or net. The integral is net area, whereas area is total area. Area and integral are different things. The reason why I'm trying to drill that into your brains really well is because they're often used interchangeably. You got to read really carefully what it is they want. They want the integral, or do they want the area? Okay, so you have to read very carefully for what you're after, and then change some signs if necessary. Okay, all of this stuff that we've been talking about, and all the stuff that's on this page, on page 275, is called, the whole concept is called Riemann Sums, and I've already referred to it as that. Notice on this page, just a quick notice, that the rectangles that they drew are not the same width. They don't have to be. They don't have to be if you understand the concept, which I already discussed with you yesterday, and I'm going to bring up again today. That's the next page, page 276. You see a little blurb about George Riemann there. As a person who is, I'm not a real social person, but I really feel sorry for George. He was the most introverted person I have ever read about or known. He was frightened of everyone. Why did he think? He was a smart man. You can, look at it. He managed to get a photograph. Can you see that with his glasses on and the way he does his hair and stuff, even for those days that he looks a little introverted? He looks introverted to me. I don't know. But he was a brilliant person. So Riemann, we call him Riemann Sums because he came up with this. And this is the concept that I talked to you about yesterday that I remember. Brent was just nodding at me the whole time. He got it. The rest of you are all going, maybe you were phased off somewhere, but Brent was nodding. Okay. This is the concept. There's two concepts, but they are exactly the same thing depending on which way you think about it. If you think about rectangles and having a whole bunch of them, if you let the number of rectangles that you put under a given space, a finite space from A to B, or from A to B from your perspective, if you want to put that in there and you divide it up into rectangles, the more rectangles you get, the closer your estimate will be. So that the actual area, not an estimate, you gotta let your mind go to infinite thoughts. So that the actual area under the curve, which is not an estimate, would be if we let the number of rectangles go to infinity. The limit, as the number of rectangles goes to infinity, would give you the area under the curve. It would no longer be an estimate. Will you buy that? It's the very, very same notion to say, let the width of each rectangle go to 0. Because you've got to keep adding more and more as the widths keep getting smaller. If you let the widths of the rectangles go to 0, you get an exact value also. So limit your widths to 0 or limit the number of rectangles to infinity is the same concept. And it will give you the area under the curve, an exact area under the curve in the limit. Follow? That's all of page 276. Moving on. Page 277. Now we're going to talk about notation, how we write things. And this is the difference, the main difference between how Newton wrote things and how Leibniz wrote things. And Leibniz put a great deal of thought into how he was going to put things together before he wrote them and published them. Newton did not. He had the idea. He put down whatever made sense to him, like kind of like that tank thing I just did, which wasn't great. And he just ran on with it. And whether his notation made sense to other people or not was irrelevant to him. If you couldn't understand what he was writing, then too bad for you. Leibniz spent a huge amount of time trying to put things together, so we use Leibniz notation because he put more thought into it and it's much more understandable. So here's the deal. I've got a circle around on the top of page 277. I've got a circle around this right here, and you may want to as well, at least until you're done with this section. You may want to look at this again before test time or quiz time. It's this piece right here that says it's got a summation notation. Remember a Greek letter, capital S? Okay, I am gonna go ahead and put this on the board so I can point and talk to you about certain things that's going on here. It's kind of important you understand the difference between the two notations and the evolution of what we use today. So I take the limit as x goes to infinity, no, n goes to infinity, of the sum from n equals 1 to an n. Do you understand that in this limit right here, I could eliminate the limit part and put infinity here? We could. But I want you to clearly understand that this is a limiting situation. And we have f of c sub k. And we're going, what? That's one part you may not recognize because I didn't talk to you about it. It was on the previous page. I didn't feel like it was important. I'll talk to you about what the part of it that's important on this one. And we're going to say that that's equal to this notation, which is what Leibniz used it, from a to b of f of x dx. And by the way, this one over here has a little bit extra blurb to it. It says that we will sum up the rectangles from, in this interval of x's. So this has to be elsewhere in the problem. Leibniz managed to get it all together in one thought. Okay, so I want you to, I'm going to read this stuff. I'm going to read this stuff and point to important information up here. First of all, before I begin, This right here means the height of a rectangle. That's located at the kth location on the x-axis. This is the height of a rectangle. In any arbitrary rectangle, it happens to be located at the k portion, the k part out there away. It's just k. So this is the height evaluated at this x value, and this is the width of the rectangle. So length times width, that's one rectangle, and we wish to sum them all up, where there are infinite numbers of them, drawn in the interval from A to B. Do you follow or not?
Will you say it again?
Yes. F of c sub k, when we evaluate a function, we're trying to find the height of the rectangle at that location. So this is on the x-axis someplace. We call it c sub k. This is an x value. And we evaluate the function we're considering at that value to get the height of the rectangle.
Okay.
And we multiply it by the width of the rectangle, which varies depending on the size of your rectangle, but that's a delta x. We will let the number of such rectangles go to infinity and add them all up to get the area under the curve. Understand the crazy notation and that it alludes to this concept? Okay, now listen to what the author says about how that became that. Listen. Notice that the difference, delta x, has again tended to 0. Because if we're going to let the number of rectangles go to infinity, this is getting smaller and smaller and smaller. Do you remember that concept that we read about Leibniz? He then decided not to call it delta x. He decided to call it dx because it was so tiny. So he's going to allude to that here in just a minute. Notice that the difference delta x has again tended to 0, become the differential dx. The Greek capital S, what you see here, has become an elongated Roman S that you see here. They're both S's, and they both stand for sum. So that the integral can retain its identity as a sum. So they're both S's. The C sub k's, meaning the x locations, have become so crowded together in the limit, this limit, have become so crowded together in the limit that we no longer think of a choppy selection of x values between A and B, but rather a continuous, unbroken sampling of x values from A to B. It is as if we were summing all products of the form f of x dx as x goes from A to B. So we can abandon the k because it's become smooth. And the n used in the infinite sum expression, we can abandon them both. So because in the limit, as the number of rectangles goes to infinity here, the widths of them have become extra tiny, and the heights of them can be found anywhere on any point of the curve. And this is the curve. This is the height at any point you choose. So this is the height of a rectangle times its width in the limit from A to B. This is so much superior conceptually than this is, because this causes you to, first of all, think back to limits and what that means. And what it means is that we're going to talk about a continuous function for heights and very, very, very teeny tiny widths. And we don't have to put this part elsewhere. He decided to put, he goes from A to B, from bottom to top. If this is your left side, this is the right side. Not always. Sometimes it's right to left. We'll talk about that in a minute. But this is what we use now to represent this concept in the limit. And this is called an integral. The whole notion, we call it an integral. If you look in the middle of page 277, it tells you what each of the parts is. The function we wish to find the area under, the actual function, which serves as all the heights, that's called the integrand. This right here, following the D, is what we are integrating with respect to. If this is written in X and this is written in Y, you're in trouble. We'll show you how to reconcile that later, but they have to be the same if you're going to proceed. We have to make them the same some way or another before you can proceed. This is a lower limit on the x-axis. This is an upper limit on the x-axis. And this whole thing tells you that we want to find the area under the curve between here and here, this curve. Okay? I beat that into you well enough? The evolution was pretty cool. Take a look at example 1. It gives you Newtonian notation, and it wants you to convert it to notation. So there's your Newtonian notation for a specific function. Can you tell me what that would look like if I wrote it as an integral? First of all, what are the limits of integration?
-1.
1 to what?
-1 over 3.
Okay, so when I say limits of integration, I mean, what are we going from and to?
It says it in the.
You'll have to look for that in a set of brackets like this. Look for it in a set of brackets, the range of values. See, Newtonian notation causes you to look elsewhere other than what you're trying to consider. You gotta go find it someplace and it distracts you. This tells you we're going from an x equals -1 to 3 underneath that curve for what?
3x squared minus 2x plus 5dx.
3x squared, what?
Minus 2x plus 5 dx.
And we put that in parentheses because it's the whole thing that is dx. That just converted that Newtonian writing into Leibnizian writing. And the reason why I like this better too is because we have enough information, or I have enough experience with this, we know exactly what we're looking at. We're looking at a kind of vertically stretched, opening upward parabola. Rather than trying to try to remember what all those C sub K's and M sub, they changed it to M's instead of C's, and you go, I don't know what that means. It's just X. It's just X in the limits. Okay, third base. Okay, now folks, here comes the next part where we're going to come back to some concepts we've talked about, and I'm going to remind you we are not doing any integrating today. Don't do that. We're not doing any integrating. What we are doing is writing areas of familiar geometric shapes as integrals, and then using what we know about those shapes to find that area. Now, here's your first example of that. Example 2 says, evaluate the integral from -2 to 2 of the square root of 4 minus x squared dx. I think I can do this over here. So hang on a minute. They want us to find the integral of what? From where? -2 to 2?
Yep.
Of what? Square root of 4 minus x squared dx. And yes, you're exactly right. This is what you must recognize as a semicircle. It's only the top half because there's no plus or minus here, right? This is a semicircle. And if we integrate from -2 to 2, that would be the radius of this circle. And so it's the entire circle. It's the entire half circle. They're trying to get you used to seeing this as being the area under something familiar. And so we would say this is equal to 1/2 pi r squared, period. So what we're doing is we're looking at the integral and we're saying that's a half circle. So what do I know about finding the area of a half circle? It's 1/2 pi r squared. And we know the radius to be 2 because that's our integration limits. So they're trying to make you make links between what you're familiar with, which is this, and the integral that expresses it. That's what they're doing. But you're not going to be doing any actual integrating. Okay. So the answer is 2 pi, and that is the area under that curve.
Where'd the 1/2 come from? Yeah.
Because it's a half circle.
Yes, that's a circle. You only have
It's only the top half. So really what this is, I guess, is half of the area of a circle, is what I'm saying. Because it's the top half.
Wait, so where'd the pi r squared come from?
Oh, really? What's the area of a circle?
I thought it was like the.
What? Okay. Are you back with us, Matt? Okay, listen up. Okay, now I want to go back to another concept. So this was a geometric solution. And a lot of what you're going to be doing today will be geometrically oriented. Now, I don't know why this author dances all around. He never sticks with one thing for a moment. We go up to page 279. Now he wants to go back and talk about this negative area concept idea thing. Okay? And he says, if an integrable function is non-positive, meaning negative or below the x-axis, then each of the rectangles that you were to find would have a negative height, and so the area of each one of them would be negative. Okay, it says Riemann sums of f over an interval a to b are negative rectangular areas. That's what he says. Okay, So if we wish to do area, now notice in the tan box that he says area, he does not say find I. He uses a capital I for integral. He's not saying find the integral. He's saying find the area. And when that's the case, you want to talk about a positive space that needs painting. But the space that we want to paint, if you look at the upper left, is all negative. And so we find the integral from A to B, which would be negative, and negativize it to make it positive. That's all. So if you're doing a negative integral, it's likely the reason why is because they want area and that integral is negative space. So we negative.
So could you just use positive from the beginning?
If you integrate from B to A, yeah.
Ooh.
We'll get there. We'll get there. Okay, hang on. Well, I want to touch on that since you guys were going ooh about it. If you're interested in something, I'll tell you. The reason why if you integrate from B to A will give you positive space if the space is underneath the x-axis is because both your widths and your heights are negative. So it flips them all around, makes them positive. All he's trying to get you to understand here is if you want the area of something that's underneath the x, you have to throw an extra negative. Because the integral will give you a negative number. Okay? All right? Let's do exploration 1. This is really fun. People love this one. So stay in there with me. It's on the bottom of page 279. I know I skipped over that next hand box, but we've already discussed it and dated it in the ground, so I'm not going to talk about it. Exploration 1 says, it is a fact, which we will prove this eventually, but it is a fact that the integral from 0 to pi of sine x dx is 2. Now you got to imagine what sine x dx looks like from 0 to pi. And it is the first loop above the x-axis. Right? So all of that space is positive. And it is a fact that the area under just the plain old sine curve without doing anything to it, this plain old sine curve, that area is 2. I'm not just making that up to make it easy to work with. It is 2. It's very cool. But it came out to be something so nice. So with that fact then, take a look at example 1, or look at number 1 in the exploration, and tell me what you believe the integral from pi to 2 pi of sine x would be. You want a picture to look at? You want the piece of sine curve with things on the x-axis to look at?
It wants the integral, not the area, right?
Yes, because it does not say a equals, it says the integral.
It's negative 2.
You think it's negative 2?
Oh, yeah, it would be negative 2.
Which one?
If we draw a sine curve here, so that you can see some things and help answer this, just a plain old sine curve out to 2 pi, one period of it. Give me a minute.
Are you kidding me?
You're not going from 0 to 2 pi.
No, because it's saying from pi to 2 pi, meaning you don't.
Oh, so yeah, it would just be the positive portion that went.
Are you talking area or
Because the area would be
or?
but the integral would be 0.
Okay, what we're saying, folks, is that this space right here is 2. Okay? Are we clear? So if we integrate from pi to 2 pi, this space will be negative 2. Okay. All right, take a look at the next one. What will be the integral from 0 to 2 pi? 0. Is everybody clear on that? We all clear? Okay, moving on. How about from 0 to pi half? 1. Because we believe in the symmetry of this. This thing comes up, comes down the same way. So if we split it right here, we're going to get half that area, which is 1. You good? Okay. How about the integral from 0 to pi of 2 plus sine x? What does the 2 do?
It makes it taller, brings it up
Yeah.
higher.
It does, moves it up. So think about that.
Is it 4? It would still just be 2, right?
No.
Is it
four? Is it double?
Yeah, it's a 2.
Oh, it would be 4.
You move it.
So yeah,
Is it
I haven't heard it yet.
6? Is it 6? 5.
No.
10. I have no idea.
4, 5. Did John say it was what pi?
No,
2 pi.
it's 2 pi plus 2.
Yes.
Oh.
It's 2 pi plus 2. Here's why. Look, if you move this sine curve up 2 and start it here at 2 and make it go up like this from 0 to pi, this part of it is 2. This part of it is 2 pi.
Wait, why is that part 2 pi?
Because it's a rectangle that is pi by 2.
Remember how to find your area.
Yeah.
Kyle's smart.
Don't tease Kyle anymore. Leave him alone.
I'm struggling here. No, that's good.
So do we all understand this? I mean, it's hard to think about it, but you can. Or you could draw it. That's what that plus 2 did, is move the sine curve up to and created this rectangle. Okay, how about the next one? From 0 to pi of 2 times the sine of x. What is 2 times the sine of x?
Makes it steeper.
Makes it, not, well, I guess steeper, right? That's a strange way of saying it, but it makes it taller.
Yeah, steeper.
Bailey's back here going. Okay, so if we draw that one, that piece of sine curve, that would look something like, from 0 to pi would go like this. And this would be 2. What's that area? Think rectangles. If you were going to put rectangles in there, how would those rectangles that you put in there differ from rectangles that you put in here?
Twice the height.
Every one would be twice as tall as its corresponding one here. Every one. So the answer is 4.
Okay.
Okay, moving on. Take a look at this one. What's the integral from 0 to pi? Oh, wait, I said that. For number 6, the integral from 2 plus pi plus, what? From 2 to pi plus 2 of the sine of x minus 2. What the? Anybody?
Pi.
What's the minus 2 going to do to it? Shift it to the right, how far? 2. And where is this integral starting?
At 2.
At 2, and where is it ending? Pi units later, so it is 2. All we did, if you look very carefully at the details, all we did is move this over to 2, and it still has the same area because we're still integrating same space. Okay? Try the next one. What do you suppose the integral from negative pi to pi is?
0.
0. Good job, Kyle.
Because they can't allow.
From negative pi to pi would be 0. Okay?
This with the sine u.
Next one. What's the integral from 0 to 2 pi of sine pi?
That makes it fatter.
No, it makes it like more condensed.
What does x over 2 do to it?
Makes it. No,
Stretches it. Stretches it horizontally. So, and it stretches it horizontally by 2. So listen up. Listen. If I draw that one, that stretch, it's going to, the new first piece of sine curve is now going to go twice as far out. So where it usually landed at pi, it's now going to land at 2 pi. The first piece of the curve is going to come down like that. So it's still at 1 because there's no change in the amplitude.
So it's 4.
I think it's 2. I think it's 3.5. I tried.
Think about rectangles again. That's what you have to think about with these multipliers, these period changes.
Twice as long.
It's 2.
Well, the width is twice as long.
Yep. If you have the same number of rectangles in this curve as you do this one, then the widths of each of these will be twice as wide, but the heights will be the same. So this is also 4. Now, what's the integral from 0 to pi of cosine?
0.
Because cosine, if you'll remember how it's drawn, cosine goes like this by the time it gets to pi.
Yeah.
That's pi. So there's as much space here as there is here, and it's 0.
It's like midpoint.
Okay? I thought that was kind of fun. Okay. I'm not gonna make it through the lecture. I think I better stop here or we're gonna run into the middle of something. But it won't take me long to finish up tomorrow, okay? And then you guys can, work tomorrow for the rest of the time. Those of you that are watching this recording, I hate to tell you this, but I've got such a little bit left that I am not going to continue it. So this is all you get for this one. Finish reading the book if you want the rest of it.